So we've got these incredible encryption tools, like AES, that are amazing at locking down a single tiny block of data, like 16 bytes. But let's be real, when was the last time you worked with a file that was only 16 bytes? We're talking about emails, documents, entire hard drives, gigabytes of data. So the real question is, how do you take that small-scale power and apply it to the massive files we use every day? That's the puzzle we're going to solve.
Right, so how do you do it? You have this fantastic algorithm designed for these little 16-byte chunks, and you have a 1 gigabyte file. I mean, you can't just encrypt the first little piece and call it a day, right? You need a system, a set of rules, a game plan for how to apply that encryption over and over again securely across the entire file.
And that game plan? It has a name, a mode of operation. It's basically the playbook for using a block cipher correctly. But here's the twist, and it's a huge one. The most obvious, straightforward play in that book, the one you'd probably think of first, is also a massive, massive security hole.
So let's dive right into that intuitive but really flawed method. It's called Electronic Codebook Mode, or just ECB for short. The name Electronic Codebook is actually a perfect analogy. Think about a giant secret dictionary. For every possible plain text chunk, there's a corresponding encrypted chunk. ECB works by just chopping your file up, looking up each piece in this codebook, and swapping it out. The key thing to get here is that every single block is encrypted completely on its own, like its own little island, with absolutely no connection to its neighbors.
The process itself couldn't be simpler. You chop the message into blocks, you encrypt each one totally independently, then you just stitch them back together. It's simple, and it has one big advantage. It's what we call parallelizable. If you have enough computing power, you can encrypt all the blocks at the exact same time. But, and this is a big but, that simplicity comes at a dangerously high price.
So what's the big deal? Well, it all boils down to one word: predictability. When you treat every block as its own separate little encryption job, you create patterns. And in the world of cryptography, patterns are your absolute worst enemy.
Okay, look at this. This slide shows the problem better than I could ever explain it. On the left, we have our original image. On the right, that same image has been encrypted with AES, a world-class cipher. But using ECB mode, you can still totally make out the original image. Why? Because every identical block of the white background was encrypted into the exact same block of ciphertext, perfectly preserving the original pattern. It's a total failure.
And this right here is the heart of the issue. The source material says it perfectly. Identical inputs lead to identical outputs. If you have data that repeats, like a patch of solid color in an image or a common phrase in a document, that repetition is going to show up plain as day in your ciphertext. An attacker can spot that kind of pattern from a mile away.
This type of flaw has a technical name. It's called deterministic encryption. Deterministic is just a fancy word for predictable. It means if you give it the same key and the same plain text, you will get the exact same ciphertext every single time. And that's the very thing we absolutely have to break.
Okay, so if the problem is that it's too predictable, the solution, well, it has to be randomness, right? We need to shake things up. We need to introduce something that makes the output unpredictable, even when the input is the same.
And the tool we use for this job is called an initialization vector, or IV for short. Think of it like a random dash of spice you add to the recipe right at the beginning. It's a nonce, a number that you only use once. By mixing in this unique random IV, we make sure that even if you encrypt the exact same message 1,000 times, you'll get 1,000 completely different looking ciphertexts. This is what we call probabilistic encryption, and it's the foundation of modern secure systems. Okay, so we have this IV. How do we actually use it to fix the mess that ECB creates? Well, let's look at our first secure mode of operation, and one of the most well-known, cipher block chaining, or CBC.
The name really gives the game away. CBC literally creates a chain that links every block to the one before it. Here's how it goes. For that very first block, you use an operation called XOR to mix the plain text with our random IV before you encrypt it. Then, for the second block, you take the ciphertext you just created from block 1 and you XOR that with the second plain text block. For the third block, you use the ciphertext from the second, and so on and so on. Now, every single encrypted block depends on all the ones that came before it. Poof, the patterns are gone.
All right, that's one way to solve the problem. But what if we came at it from a totally different angle? Instead of directly encrypting our data, what if we used our powerful block cipher just to generate a long, random, one-time use key?
This approach basically turns our block cipher into what's called a stream cipher.
The block cipher's new job isn't to encrypt the message itself. Its job is to act like a random number generator, pumping out a stream of key data. Then, you just take that key stream and XOR it with your plaintext. And here's the really cool part. To decrypt, you do the exact same thing. You generate the exact same key stream and XOR it with the ciphertext. You never even have to use the block cipher's decryption function at all. So the first way to do this is called Output Feedback Mode, or OFB. You kickstart the process by encrypting the IV. That gives you your first chunk of the key stream. Now, here's the feedback trick. You take that output you just got, and you feed it right back into the machine as the input for the next round. You just keep feeding the cipher its own output over and over again to generate this long, random key stream that's completely independent of the message. Now, cipher feedback mode, or CFB, looks almost identical at first glance, but there is one crucial twist. You still kickstart it by encrypting the IV, but to generate the next block of the key stream, you don't feed back the cipher's internal output. No, you feed back the actual final ciphertext, the encrypted message you just produced. It's a subtle change, but it makes a world of difference in how it behaves.
So let's just nail this down, because it's important. In OFB, because you're only feeding back the cipher's own output, the keystream is totally independent of your actual message. You could generate the entire thing ahead of time if you wanted to. But with CFB, the keystream depends on the message because you're using the ciphertext from the previous step to create the key for the next one, a really critical architectural difference.
Okay, that was a lot to take in. Let's take a breath and put all 4 of these modes on the table, side by side so we can see how they all stack up.
So here it is, all laid out. You've got ECB, the odd one out. It's deterministic, it doesn't use an IV, and that makes it dangerously insecure. Then you have the others, CBC, OFB, and CFB, which are all probabilistic, and that's thanks to the IV. CBC is that classic chaining method that encrypts the data directly, and OFB and CFB act like stream ciphers. The big takeaway here is that everything except the broken ECB mode introduces some kind of sequential dependency. That's the price you pay for real security.
So, we figured it out. We know how to keep our data secret, even for huge files. Modes like CBC, OFB, and CFB fix the glaring holes left by ECB. We've got confidentiality, but there's still a piece of the puzzle missing. What stops an attacker from just flipping a few bits in the ciphertext while it's in transit? These modes won't stop that. They protect secrecy, but not integrity. To solve that problem, you need another layer, which gets us into the really interesting world of authenticated encryption. But that is a story for another time.